Hello and welcome to Tech Decoded. I'm Henry Gabb, editor of the Parallel Universe, Intel's quarterly magazine for software innovation. Today I'm here with Geoff Lowney, senior fellow in the Intel Architecture, Graphics, and Software Group. Today Geoff is here to talk about a new programming language called Data Parallel C++. Welcome, Geoff.
Glad to be here, Henry.
So Geoff, Intel just released Data Parallel C++, a new language for heterogeneous parallelism. Why are we going with a new language?
Well, you have to first think that data parallelism or data parallel compute is sort of the dominant compute pattern of now and of the next maybe 10 years. All of the new areas, AI, machine learning, video processing, these are all data parallel computation. And we need a language that will make it easy for a programmer to express data parallelism. So we're starting, though, with C++, and we're extending it. So data parallel C++ programs are all C++ programs. So in some sense, it's not a new language, but we're adding these new ways to express parallelism. And if you build the language with a data parallel C++ compiler, then the data parallel regions can be offloaded to an accelerator and run in parallel.
Can you describe the parallel programming model?
So the basic data parallel paradigm is that you have millions or billions of data items in your data set, and you want to do similar or maybe identical computations on each of them. So this language, data parallel C++, is set up for that, for bringing data in and doing similar computations across very, very many pieces of data.
Does data parallel C++ require me to have separate host and kernel code? Do I need to write and maintain a separate kernel for CPU, GPU, FPGA, and whatever architecture is coming?
Well, there's sort of two issues here. One, the nice thing about being based on C++ is that you can structure your program the way you'd structure a normal C++ program. You can put everything in one big file, you can split it up, but there's no requirements based on the language. Now, targeting different accelerators, our philosophy is that you're expressing a data parallel algorithm. The expression of the algorithm should be roughly portable across the accelerators. However, the different accelerators have different degrees of data parallelism. For example, a high-end Xeon CPU has, say, 28 cores with SIMD units, whereas a high-end GPU would have hundreds or maybe 1,000 cores with SIMD units. So when you're targeting a discrete GPU, you need to express or you need to say that you want more parallelism, more things running in parallel than you do on the CPU. So you need to tune or parameterize the parallelism differently. But the basic expression of the kernel should be the same, and I don't think you'll need n copies of the program.
So why didn't we just go with OpenCL or even Cuda for heterogeneous parallelism?
Well, OpenCL is great technology, but if you've ever written an OpenCL program, you know that it requires a pretty low-level detailed programming, and it's not very productive. So we wanted to bring the benefits of C++ productivity to this area. And in fact, the Kronos Committee, that's the group that has developed OpenCL, has made the same decision, and they've introduced a language called SYCL, which brings C++ to the OpenCL space. And our language is based on SYCL, so that we are working basically with the OpenCL committee on how to move forward. Now, as for Cuda, Cuda is a proprietary language, and it's really only focused on programming GPUs. So it's not a good language for cross-accelerator, and it's not a good language for cross-industry. So it really wasn't something that we pursued.
Okay, so data parallel C++ is built on C++11, which is modern C++. How much does data parallel C++ require using those modern constructs?
Well, we do use the modern C++ for launching a kernel. But that's only one part of your program, and actually only a few lines of code. So there is a small part of your program that will have to use these newer features of C++. But for the rest of the program, including the kernel or all the host code you have, you can write it in C or traditional C++ or use modern features. One of the nice features of what we're doing is that it lets you use these high productivity features like template functions in the data parallel kernel, so that you can write with C++ in the data parallel kernels if you want to. But if you're a C programmer, like maybe you are, you can stay with C.
Okay. So I don't really have to update my legacy C++ programs that much.
You don't really need to change the language. If you want the program, though, to run in parallel, you have to rethink it and make sure that the inner loops can be expressed in this data parallel fashion. And that's the challenge, actually, of bringing any program to an accelerator or to a parallel environment. It's really not the language itself. It's how you think through the problem and make it parallel.
And so based on that, I can theoretically, or in reality, can I combine data parallel C++, oneMP, parallel standard template library, and maybe threading building blocks, all in the same source code?
Yes, you could use all of those technologies. And both on the host side, as we were discussing before, data parallel C++ is really C++. So we provide a standard C++ environment, so all of the technologies that run in C++ will work there, TBB, openMP, and so forth. Now on the accelerator side, we're basically defining a standard for how to launch a kernel and run it in parallel on an accelerator. So data parallel C++ is our major way of doing that. But for example, for parallel STL, we're defining a new execution policy, which will let parallel STL algorithms run an accelerator. And for openMP, at least for Intel, we're taking our openMP offload and mapping it through the same compiler and runtime. So you can, on the accelerator, use all of these technologies at the same time as well.
So DPC++ is an open, evolving language. What features do you see coming in the next few years?
Well, the first feature we're adding, and we're doing that today, is unified shared memory. So a lot of modern accelerators, the host will have its own memory and the accelerator will have its own memory, and it can be a real struggle to manage that data. So we want a common address space across those two distinct memories, and the ability for you to program with pointers and have a pointer to an address mean the same thing whether you're on the host and the accelerator. So this means you can use pointer-based data structures and move them to the data parallel kernels or not, and it makes programming much simpler. So that's sort of the basic thing we're doing as a productivity feature. Now looking forward, we're going to evolve the language as hardware evolves. Now we're in an age where there's a lot of change now. That's why we're doing oneAPI, actually. So for example, neural net accelerators, the core to a lot of AI, those are becoming much more programmable. And they're actually in hardware putting capabilities of doing convolutions and other linear algebra expressions. So in the language, we will add a new data type, a tensor, which is really a high dimensional array, and provide operations, high-level operations, to operate on those tensors directly, and then the compiler will map it to the hardware. So that's one direction. And then for spatial architectures like an FPGA or some other ideas that we've been thinking of, you really want an idea of a channel or a pipe so that you can write systolic operations which can communicate. And so that's another direction that we'll be going in the next year or two.
So with unified shared memory, I don't have to worry about moving the data back and forth between the host and the accelerator?
You don't need to if you don't want to. So
Okay.
this now becomes a performance issue. So you bring the program up, data can migrate, but then the key data transfers, and this is perhaps the most important performance issue, you need to plan those out ahead. But that's a problem whether you have this pointers or copying or whatever. In parallel computing or high performance computing, making sure the data is ready when the compute is ready is the hardest problem, and you're going to have to address that anyway.
Yeah, because I can remember the data sloshing that would just wreck performance if I wasn't careful about when and how I move data between the host and the accelerator. So DPC++ is an open, I guess, industry standard language. What contributions would you like to see from industry?
So we're looking for industry to work with us and to be equal partners. We're doing everything here in the open. We're doing the specification in the open, and we're doing our implementation in the open. And we have a website where people can contribute. We have one or two industry contributors already working with us. We're also working with the SYCL Language Committee, which is part of the Kronos group, the group that brought OpenCL. So we're working with them and with some other external people to try to bring all these ideas together. So going forward, as the project gains momentum, I think we'll get more and more industry collaborators.
Do you think the data parallel features will ever be will ever become part of standard C++, which would render DP++ obsolete?
Well, let me answer that in two stages. So I do believe that data parallelism will move into C++. But C++ is a very big language and a relatively old language. It was developed in the early 80s and has been extended since then. It has a lot of different constituencies, a lot of different groups that want features. So it's hard for it to move very fast because it needs to get consensus and everyone buys in. So data parallelism will appear, but it will probably take 5 to 10 years for the features we're showing now to end up in the language. So if you roll the clock ahead 5 or 10 years, yes, we'll have today's features in the C++ standard, but hardware will have evolved. We'll need new language features to support that hardware, so we'll be in the same position we are today. We'll have some advanced features that we want to get into the standard.
That's right. You and I, we live in a parallel computing world, so we forget there are other people using
That's
C++
certainly true.
who have different priorities. Okay, well, before I let you go, do you have any quick tips for developers?
Well, this is a pretty exciting time, I think, to be a developer in this data parallel space. There's a lot of work in algorithms going on, in AI and so forth, and the hardware is changing pretty rapidly, and we have this programmer in the middle. Now, you'd like to say that the magic compiler can do it all, but compilers can only do relatively simple things, and we still need the programmer to make this mapping between the algorithm and the hardware. So it's a pretty exciting challenge. And I'm thinking with the language we're developing, we'll make that easy. And, it will let programmers shine. And so I think it'll be fun and, happy hacking.
Well, thank you, Geoff, for sharing your insights today.
It's been a lot of fun, Henry. Thank you.
I'm Henry Gabb with Tech Decoded. Please visit our website for more information about data parallel C++ and oneAPI.
Hey everybody, I hope you liked this video. If you haven't seen our other videos, make sure you remember to subscribe to the Intel Software YouTube channel. Don't forget to leave us a little comment down below as well to engage with the other enthusiasts who watch our shows.